Good morning. Happy to see some brave souls on this cold Saturday morning. I know there were also some issues with the trains, so maybe some people might still hop in later. Today, as you might recall, we have our 5th session, and this is also the very last, more theoretical lecture, where we will explain, we will discuss things, but overall those lectures are more theoretically based. As of next week, next week, I think it's next Wednesday, we will completely shift gears, have another approach where each time we will briefly discuss a certain technique in order to bridge this business IT gap that we discussed in lecture 1, and then we will make some exercises on that. And so, again, sketching the overall picture. Lecture first, we introduced a little bit why it's important for you as managers to study informatics. We discussed some very important topics like the business IT alignment gap, digital transformation, this study from the Standish group, the chaos report. We looked at things like the IT productivity paradox and so on. In lecture 2, we studied the basic main categorizations of enterprise information systems. Horizontal typology, vertical typology, as well as those management challenges related to that. Session 3, the development. How do we actually build them? The several stages, the waterfall model of the system development lifecycle, the iterative model, and then last time we explored a little bit what it actually means for your business in terms of your business model, both in terms of e-business, where we covered or we try to apply management theories such as Porter's 5 forces model, the transaction cost theory, agency theory, but also e-commerce side of the picture, where we looked at the typical characteristics, the omnipresence, the complexity of the information that you share, the amount of information that you share, and so on, as well with some practical examples. And today, that last more theoretical lecture will focus more on some trends, evolutions that we currently see in the business informatics landscape. And the problem is that each of the topics that we will discuss today, in fact, they deserve their own course. So I will be obliged a little bit to just scratch the surface. On the other hand, I also didn't want to completely cut it out, because when you enter in companies, when you are working or will start working, you will without any doubt be confronted with some of those terms. And what I want to do is to demystify some of those things, because there are a lot of misconceptions, there are a lot of misunderstandings about these concepts, these trends. And when you look back in 10 years to this course, maybe this is the most variable part, in the sense that all the other things are generally accepted theories and concepts that already exist for several years. This is more volatile, this is more changing. Maybe some of the concepts that we discuss here are left behind in a few years because they didn't prove to be so successful. Others will maybe have only become more important. But as I said, the goal is to let you understand the basic principles, the basic mechanisms, to demystify them a little bit, so that once you come into a company, you more or less understand what it's about, and that you're not overwhelmed by these concepts, and at least you can follow the general discussion. Okay, computer says no. What's the problem? Okay, we're back. Is it? Also share my screen before I forget. Yeah. So, given the time span, we will not be able to go very deep into each of those topics. So what I did is I tried some of them to put more emphasis on them, and some of them we will only be very, very brief, 1 or 2 slides. Choosing is losing. I needed to put some emphasis. What I've chosen for is to mainly, I mean, I want you to understand at least some basic principles of things which are very much discussed today. So we will go a little bit more in depth on blockchain, artificial intelligence, and we will also take, if we have enough time, we will also look a little bit at the management aspects of security in an organization. The other things we will go much more briefly. And in comparison or in contrast with the previous lecture, so like the whole story from A to Z or to Z will be a little bit less strong because we will just go through several topics. And in the end, I will try to bring everything together. But in the lecture itself, yeah, it might be hopping a little bit from one to the other. But let's see. You can interrupt me at any time if you think there's something not clear or you want to have some additional examples. Feel free. We start easy. We start with a little bit of warm up. The idea of cloud computing, most of you probably already understand or know it. What I want to do is to bring a little bit more nuance in this discussion. Yeah, it's really having a hard time today. Blah. So what cloud computing is actually about is that there's this general reason that whatever we need in order to do computing, whatever we need in order to build software systems, that we can actually tap that from the cloud. So that involves hardware, software, and even business processes. This is the idea that you might also recall in that very first paper that I suggested you to read from Nicholas Carr, IT Doesn't Matter. If you already started reading them, and which I strongly encourage, then you might see that this idea of Nicholas Carr very much aligns with his idea of cloud computing in the sense that he also basically argues IT and a lot of aspects of IT, they are not so special. They are not so difficult, so to speak, because you can just tap them from the cloud, just like you can tap electricity from your electricity socket or water from the tap. It's something that you can tap from, in this case, the cloud. So as soon as you have an internet connection, you can get certain resources from that cloud in order to do your operations. And so that means that the provisioning of those things is considered as a commodity. And that is also the term that actually Nicholas Carr uses in his paper. So you only need the right connection. You don't need to update, install, maintain those things themselves. And so what you see is an evolution from doing things on-premise, which is the term which is used when companies have the servers in their own offices, on their own sites. They provide or they buy software often based on licenses, and you actually go offsite because you actually even don't know where the servers are, where the hardware is placed. You always are not always super or fully aware of the software that's running on those hardware devices, because you also want not to be involved in that. You just say, I want to have a certain service and this software needs to run, and all the other complexity needs to be dealt with by the cloud computing provider. There's a definition commonly, most frequently used by the National Institute of Standards and Technology, which is nice in the sense that it also lists the basic characteristics of this cloud computing philosophy, where we say cloud computing is a model for enabling ubiquitous, so you don't really see it, it's somewhere in the cloud. You don't know where. It's convenient, so you just need to plug into the internet, or you can even do it wireless. On-demand network access. On-demand means that you get the hardware, the software, the scalability whenever you want, and also in the amount or the degree that you want. So you can upscale, you can downscale, you can have more customers visiting your website, and then automatically additional services will be added, or you can have calm periods after the Black Friday weekend where you can decrease your services, and it's on demand. So you can increase it yourself, you can decrease it yourself, not too much need for human intervention. What you need is, well, you need to have network access, so you need broadband internet, so you need high-speed connections, which in the Western world most companies and people today have, and it's based on a shared pool of configurable computing resources. That means that the big cloud computing providers today, typically Amazon Web Services, Google, or Alphabet, Microsoft with their Azure platform, What they provide is huge resources, and they pool those resources in the sense that it might be that you, with another customer, you are using partly the same network service, or you're using different ones from the same server rack or the same data warehouse, server warehouse. You don't know, but there's a big pool of resources, and that is shared. So depending on who asks what at a certain moment, those resources are allocated to the different clients. Can be rapidly provisioned. As I said, you can quickly upscale, downscale, and minimal management effort or service provider interaction. The goal is really like, I just want to have these kind of resources, and all the rest, all the complexity, I don't want to care about. I don't want to care about the physical security. The Amazon premises, the Microsoft, the Google premises, they're super well protected, so you don't need to worry about physical intrusion of people into your computer centers, because that will be dealt with by your cloud computing provider. Now, the nuance that I wanted to bring into that is that when people talk about cloud computing, they often think as it's like it's one big thing. Whereas there are different ways to engage in this idea of cloud computing, in the sense that you have the most basic form, which is called an infrastructure as a service, meaning that you get hardware and network, service, storage facilities. As I said, the cloud provider takes care of all the practical arrangements for that. So they will make sure that there is a server, that there is physical security, that they put it up and running. But it will be very basic. So their actual operation of the systems is still to be done by the end user. So you will be able to access that server, but you still will need to install the operating systems, all software that you develop to put onto the operation system, what you want. So basically, you can just hire a server at a certain company with a certain capacity, and that's it. You can go also one step further, where you say, well, I do not only want to have kind of the infrastructure, the hardware, but I also want to have some kind of basic software running on that. The operating systems, like, do you want to use Windows? Do you want to use Linux? You choose that. And often it also comes with a set of modules or libraries which you can use, for instance, to deploy Java software, Python software, whatever. So some kind of repositories, as they call them. So you get the infrastructure, the servers, plus standard applications. And often it's like a little bit of a shopping list. So you can say, I want a server with these capacities and Linux of this version prepared to run software in these and these and these programming languages. So you can pick and choose a little bit. But so you have infrastructure plus boilerplate code, as it's called. You can even go one step further, where you say, I do not only want to have the server, I do not only want to have the basic software that needs to run, I also want the actual software, the applications that we're going to use as end users, to be deployed, to be ready on those systems, and to be accessible for me as a customer. So could be an application to a web server, for instance, where you actually have already a server set up with all the operating systems and the web server itself, so that you can host your website there. Or you can have email services like Outlook and Gmail. You basically go there and you can access and read your email based on those services. In a more business environment, you have complete CRM systems. Like Salesforce was one of those, the one who did that, who started that business ID quite prominently, where they said, well, actually, you don't need to install any CRM software yourself anymore. We will provide the servers, we will provide the boilerplate code, and we will actually have a fully installed Salesforce.com application running there. And you just sign up, you say your company name, and you provide the amount of access users that you want, how many users will use your software. And then depending on your use, depending on the time that you want to use the software, you pay. And so for the rest, you don't need to be concerned. And you can even go one step further and actually go to full business processes as a server. Some people would say, well, it's not really cloud computing anymore. Nevertheless, Gartner would still consider this as part of cloud computing, where we don't only have the infrastructure, we don't only have the basic platform, we don't only have the software, but actually the business process itself, where you can have, for instance, a full e-commerce printing service. Like the last time we were discussing business models, and we said, well, nowadays you can have companies where you just send your PDF file, and the booklet will come out, will be printed, and will be sent to the customer. Well, that is something that is an example of business process as a service. Yeah. So cloud computing, it's important to understand that the idea there that we consider IT resources really as a commodity, as a readily available resource, can be upscaled, downscaled on demand. Only thing you need to access it is the internet, and it exists in different flavors: infrastructure, platform, software, and business process. What do you recognize? What is common in all those titles? Which words are common in these titles? As a service, indeed. So the reasoning behind it is that you make the transformation of buying something and then you own it towards getting something as a service. Like for water or electricity, normally you pay for the amount of usage that you make of it. So actually it's a service to you. You can use a lot of water, little water, and depending on how much you use, you will pay more or less. The same idea is often applied to cloud computing, where the idea is you don't need to buy the server, you don't need to buy the licenses to use it. You just pay as you consume. The more you consume, the more you pay. Yeah? That's the underlying idea. So if people talk about the cloud, well, that's more or less what they mean. That's more or less what they relate to. Yeah. Today it's well integrated in a lot of companies. So probably most of you already know that, but I wanted to bring in those nuances. Yeah. Any questions? No? All right. And then, as I said, like we really hop from one to the other. We will dive a little bit more in this idea of blockchain. Again, a lot of people talk about it today, and it has kind of this hypey way of working. Some months it's very popular, other months people say blockchain is dead, and then 2 months later they again start talking about blockchain. But the chances that it will again be hyped again in the next few months are quite high. So I think it again it's good to demystify a little bit what it is about. When people talk about a blockchain, well, and they more or less have a little bit of knowledge what blockchain is actually about. Actually, what they want to say is they're talking about a decentralized ledger or a database, as we said in the first session. What is a database? A database is something that stores information, and there are different ways to set up a database. One way to do that is by means of, and we will see more specifically what it means in a minute, by using a decentralized ledger. A ledger is kind of a list of things, like when you're doing accounting or bookkeeping. You have also, people also talk about ledgers. You have transactions, what you have paid, what you have sold, what you have bought, and so on. So a list of transactions, a list of items. So it's a ledger which is stored in a decentralized way. So not central, but decentralized. We'll be more specific in a minute. And it happens via a block or via sets of blocks. Blocks in a chain, actually. That's why they call it a blockchain. It's a chain. It's a sequence. It's a chain of blocks. And in each of those blocks, you have transactions, items, and we will store them in a decentralized way. What is the reason why people talk about this idea of a blockchain? Well, the idea is that in traditional database systems, in traditional formats of storing information, you have one point where you store all the information. Maybe you might have a backup for if something goes wrong with a central storage point, but the idea is you have one source of information, And if you want to know something, or if you want to add some information, you go directly to that central point of information. When people are talking about a blockchain, they say, well, first of all, we want to have a chain of blocks, but we will also not have this centralized way of working. We will have decentralized, meaning no central controlling entity. So there will be not one database which is accessible for people, where you can read and you can put additional information. No, it will be distributed. It's a little bit like, I try to visualize it. It's like this is the traditional way of working when in database systems, when you have business or enterprise information systems, where you have all kinds of nodes or entities, people, companies, basically something that wants to have access to certain information. They want to read information, they want to add information, and they all go to this central controlling entity, your database, classical system. And so this is centralized, clearly. And the idea of a blockchain is that basically you just delete this. This central entity doesn't exist anymore. And how do we then cope with storing the information? Well, then the solution is we will not just store it centrally, we will store it with all of those nodes, all of those people who actually want to use the information. Well, they will have the information themselves. They will have the ledger, they will have the transactions. To make a little bit of an easy, imaginable example, suppose that you're playing some kind of a cards game with your friends. One solution is that you say, well, we are playing with 4 or 5 or 6 people, and one of those people, he or she will be the central controlling entity. He or she will keep the scores of the game. So you have different rounds, and each time, the first time person A wins, and you write down the score, and the second time person B wins, and then you write down the scores. But there's one person who's responsible for writing down the scores. It's a centralized system. You can also go to a decentralized system where you say, well, we will not do that. We will not have one person who's responsible for keeping the scores. We will all have our own notebook, and we will all take note of the different scores. So each time that a certain round is completed, we note down the scores of the game. That's a decentralized model. Now, what is the benefit of going from this to this? What's the benefit that you do not have one person noting down the scores, but everyone in the game noting down the scores? Any ideas? Because it's more effort. Everyone needs to note it down. And I mean, here you have one person, here you have all the persons doing the same job. So why would people actually opt for this model? More security, and you said, what's this? No control over the process from a central point of view. Yes, indeed. Security, control. The main reason it's indeed it's perfectly in that direction. The idea is trust. If you have this central controlling identity, you need to trust that person. If he or she is not honest, if he or she messes up with the scores, after round 24, you don't know anymore what happened in round 2 or 3. So you look at the paper that one person was writing down. And if he or she was messing up with the scores, there's no way to solve it. You need to trust that person. If you all note it down, it's much, much more difficult to trick the system. It's much more difficult to write down other scores than what in reality happened, because all your other friends, they will have noted down the same, and they will say, that's strange. So you scored more in that one round, but all the other 5 or 6 friends, they noted down a different score. So they will know for sure that you were cheating. And so the main reason why people said, well, let's go from a centralized storing mechanism to a decentralized storing mechanism is the issue of trust. In cases when you do not have the situation where there's one entity that you can trust, then one solution might be to have much more effort, to have everyone involved, to everyone noting down the things, but then at least there are multiple versions, and the truth is determined by looking at what everyone is saying here. So you can compare versions. And so with the blockchain, there will be no central controlling entity. And to make things more complicated, I mean, here, of course, you might still have the tendency that people, they start working together. And some people, they say, well, we're not going to cheat with one person, we're going to cheat with two persons, and so on. So there are some complications there. And the idea is that in order to make it really secure, in a typical blockchain, and there are different versions, so I use the word typical, in a typical blockchain, there will be some complex algorithms that are used, hash codes that are used, to make sure that it's not so easy to just add transactions. Yeah? It needs to be validated to make sure that it's really, really correct, in the sense that a lot of effort needs to happen. You need to prove often that you have done a lot of effort to validate the new block to the blockchain. And if it requires a lot of effort, well, then the chances are much, much more unlikely that you're able to easily tamper, to easily cheat with results. I will make it a little bit more specific in a second. But that's the general idea. Yeah? Blockchain is a chain of blocks, so one after the other, chronologically. In each of those blocks, you store some kind of information, most likely and most frequently transactions. You do that in a decentralized way, so not a central database. You do that because there's no trust, or you do not want to trust one central entity. You want to have it dispersed, decentralized, and often you also have some kind of a validation mechanism, a verification mechanism via complex algorithms that make sure that it's not easy to mess up the chain, or even impossible. Let's make it a little bit more graphical. Suppose that the most well-known example of blockchains are still today currencies like Bitcoin and or other cryptocurrencies. Suppose that at a certain point in time, you have your chain and you create another block. What does this kind of block represent? Well, you will have preceding blocks, block 22 until 1. And so you give that block a number, you give that number a timestamp, you give that block a timestamp today at this hour and this minute and this second. And then within the block itself, you will list transactions. For instance, this amount of Bitcoin goes from this account to this account. So amount to from, and that's it. And you will not have just one transaction, you will have multiple transactions, and you label them to make sure that you know where they belong to. And so we said a blockchain is a chain of blocks. So this is one block, but you have a chain of blocks. So you also make block 24, which looks similar, but has other transaction data, of course, and block 25 until how many blocks that you want. You will also connect them because we said these are blocks and these blocks are connected. So there are some arrows. There's a link. Each block will link to the previous one and saying, well, I am block 24. Meaning that I follow upon block 23. And what will happen is, as I said before, we have chains of blocks. In that block is information, but we want to make sure that it's secure, that it's not easy to mess up with. So we will use a hash code to protect it. What is a hash code? A hash code is something that stems from security in computer science, and it's basically one way to represent it is like this, where you can take any kind of information, any kind of document, as long as it's digital, and that's a nice thing about information systems. In the end, as we said before, in this big gap, in the end, it's all zeros and ones. So whether it's a PDF document or a video or an image or cryptocurrency transactions, you take a document and there are mathematical functions which are called hash functions, and they will transform your document into a string, a set of characters. And I mean, this is, for us humans, it's non-interpretable, but it's just you can have lots of information, megabytes, gigabytes of data. When you apply a hash function, you transform it into a set of characters, which is called a string. These mathematical functions, which are used in encryption a lot, they have some benefits. Depending on the algorithm that you can use, you can determine how long this hash code will be. But the most interesting is that these are mathematical functions that only work in one way. In mathematics, often when you have an x variable and a y variable, if you calculate the y based on the x's, you can often make the other the calculation the other way around as well. So based on the y, you can also determine the x. In hash functions, they use encryption functions, hash functions, which do not allow you to calculate the other way back. So that means that if you have an original document and you apply the hash function and you get this incomprehensible string, that means that it only goes that way. If you only have this outcome, even if you possess the hash function, you will not be able to reconstruct this document. You will not be able to tell what was exactly the source document. What you can do is you can take another document, you can apply the hash function, and you can see whether it results in the same hash output. So you can see, okay, something was stored. I apply the hash function, and this is the result that I get. I know that it is a one-way function, so the input will be converted into this. It will always be the same, but you cannot do it the other way around. So if you know this, you know, okay, I have a document, I have applied the hash function, I get this. I cannot just return to this one, but I can upload a document. I can apply the hash function, I can see what comes out, and if it's the same code, well, then I'm quite sure that I have this document which was stored. The nice thing about these hash functions, except from the fact that they are one way, is also that they are very sensitive to changes. If you take this PDF document and you change 1 or 2 characters, this hash function, will look completely, or the outcome of the hash function will look completely different. And so that is interesting because we said before, okay, it's about trust. You don't want people with tampering with things, messing up with things. So as soon as someone is messing up with the file, the output of the hash code will be different. And so that's interesting for our purposes, because if we have blockchains and we want to make sure that nobody messes with one of those transactions, one way to secure that is by using hash functions. Yeah? Because as soon as someone tampers with this, we will see, the output has changed. We know that something has been wrong with this. Yeah? So there will be blocks. They are changed because they have a link with the previous one, and each time a hash code will be calculated based on all the information that's here. So the block with all its transactions, the content, the block number, the timestamp, as well as the link to the previous block. And for each time that you add a block, this hash code will be calculated. Then this complete ledger, so this complete chain of blocks, will be stored on all the nodes, all the participants in the network, all those computers. All those nodes, they have their own block or own version of the blockchain. And then the question is, how do we determine what is true? Because even if you have hundreds or thousands of people who are in the network and they have their own instance of this blockchain, well, there might be different versions. And then we still haven't solved the problem, because then which version of that chain do we trust? Well, most commonly, the idea is that there's a consensus algorithm saying that the longest chain in the network is the one, or the longest chain that's available on the network is the one that we trust. And that might be strange, because you might say, why should we trust the longest one? Because I can easily add more and more and more transactions, and I can tamper here with some transactions and make sure that the block is just, or that the chain is much, much longer than all my competitors, so that I can claim the truth. The only way that I should do is I mess up with some transactions, I make sure that a lot of money goes to me, and then I will just make sure that that I add a lot of other imaginary blocks with transactions. I have the longest blockchain, and so I claim the truth. Well, there's one way, or one additional element that we need to consider in order to understand that. That is that certainly when you have blockchains for currencies, there is a mechanism that requires proof of work before you can add a block. It's very difficult, it's very resource intensive before you can add another block. That's what is, and I used here these blue squares to indicate that. That's because actually there's one more thing that is added to this package, that's added to each block, and that's called a nonce. In order to understand it, we need to go back to this one, the hash functions and the nonces. Because this document, it's actually this, all the information we have here. The block, the timestamps, transactions, the link to the previous one, and so on. But we will add this blue thing here, which is the nonce. And the idea is as follows. We already know that we can convert any digital document, any digital file into a hash output by applying a hash function. The idea in blockchains is often that we take that document and we add the nonce, a numerical value. Of course, I've abbreviated everything here. In reality, those strings are a bit longer, and also here the nonces are longer. But this nonce is not determined up front. This is something that you, as a node in the blockchain network, need to find out yourself. And so this proof of work consists of those nodes who think, okay, I want to add some additional information to the blockchain. Well, this proof of work consists of guessing what the adequate nonce would be. So what they will do is they will take the blockchain up to that point. So they will say, suppose that I want to add this block. I take this information, this document with all the transactions, timestamp, block, link to the previous one, and so on, and I'm going to guess this nonce. I can do a first attempt and I get this hash output when I apply the hash function. I can have a second attempt and I get this output. Now, the tricky thing is that a blockchain algorithm will often give you a difficulty requirement. A difficulty requirement for the output of your hash function. Meaning that, I mean, if you just go randomly here each time, as I said before, you will get a different output. But the difficulty requirement, for instance, would be, well, all nice, but you need to make sure that the output of your hash function has, for instance, 11 leading zeros. And that's very difficult because, as I said, hash functions are unidirectional mathematical functions. Given the input, you can calculate the output, but based on the output in the hash function, you can never restore the input. Meaning that if there is this difficulty requirement, we want that the first 11 characters of this hash output are zeros. Well, there's no easy way to find that out because we cannot apply the function from the output to the input. We don't know if there is an output that should start by 11 zeros. We don't know what the nonce should be, what kind of characters we should add to the document in order to end up with this. The only way to do that is by what's called in computer science brute force mechanisms. So the only way to make sure that at some point you end up with a hash function that has 11 leading zeros is to take the document, to take the block, to take the chain of blocks that existed before, to add nonces, to try out several things, to try out several variants. Each time you calculate hash function and you see, does this fit the difficulty requirement, yes or no? And at a certain point in time, by pure luck, by trying many variants, suddenly it will be that this new block with the new information plus a particular nonce will suddenly result into the output from the hash function with 11 leading zeros. And why people say, well, this is a proof of work is, well, in the end, it's proof of work. It's the result of the fact that those computers, they need to try out a lot of versions, a lot of attempts, because as I said, it will not just be 6 characters, it will be much more characters. And so the amount of attempts that you need to do to come up with a hash output that suddenly has 11 zeros, that takes a lot of time, that takes a lot of effort. And so then hopefully it becomes clear why it's so difficult to mess up with the blockchain. Because if we go again here and we have blocks with a nonce, we look at the hash code. We want to add another block with all the information on it, the link to the previous one. We need to find a nonce and to have a hash code. Again, we want to add another block with all the information with it, the link to it, and a nonce code. That thing that I said, well, okay, how do we determine the truth? The truth is the longest chain. And then just to mess up with something and then add additional blocks, it doesn't work that easy, because you always need to calculate those nonces. If you would mess up with a transaction here and you want to make sure that you get all the money, well, the only way to mess up with the system is to change a certain transaction here and then do all the work again, because you can only start from here. You need to figure out that nonce yourself. Then you need to add that other block. You need to figure out another nonce yourself. You need to add another block, figure out the nonce yourself, and publish it. And then you need to figure out another block, find the nonce, and then have the hash code, all complying with this difficulty requirement. So messing up with a certain transaction will cost you a lot of effort. And so the only way to mess up with the system is to have processing capacity, which is way larger than all your competitors. Then you might trick the system. But otherwise, you really need to trust upon the network, upon the community, because there's no way on your own of messing up with a transaction, each time doing this whole game where you have information, you need to find a nonce until you get a compatible one, and then add another block, find a nonce until you have one which meets the difficulty requirement, and so on. Now, does that make sense? Yes. Doesn't make sense. Yeah, very good question. So why do we add a nonce? This nonce is the thing that you need to come up yourself as a node in the network. Yeah? So what you know up front is this information. You have the block with transactions. Say this person puts money to this person, this money to this person, this money to this person. That's information that you, as a node within the blockchain, you know. It's a file, and it's a set of transactions, and we want to add it as new information to the system. This blue one, you don't know. If you want to add the block to the blockchain, you know, you see all the transactions that happened, but this one, you need to figure out yourself. It's only possible by trying. So you make up yourself a number. You try one. And then you see what happens. And most likely, it will not be conformant with the difficulty requirements, because you try a random number, you imagine it yourself, you try it out, and you see, but it doesn't work. Damn, I need to give it another try. I try another number, and I see, does it meet the difficulty requirements? Still, again, it doesn't work. And I try again and again and again. This might take a lot of time. This might take seconds, minutes, hours, days. You try and you try and you try with other nonces, because you don't know what a nonce is. You need to find it out yourself. You need to experiment. You need to do one guess and another guess and another guess. It's like I have an imaginative number in my head, 1 between 10 billion, and I ask you, give me the number. And you will do one attempt, you will do a second attempt, you will do a third attempt, and you don't know how many attempts it will take. At a certain point in time, might be very quick, might be very, very much in the future, suddenly you will find the right number, and then it says, okay, it's validated, you can go. Yeah? Yes, so what it's done basically by computers in the network. As we said before, the idea of a blockchain is that you do not have one computer, one database, which is storing the information. You have many nodes in the network. You have many computers in the network who all store that information. And all those computers, they will start guessing. They know these transactions have taken place in the network. We want to add it to the truth. We want to add it to the blockchain. So all those nodes, all those computers, they will start guessing. One of them will be the first one. The first one who gets it, and he says, I found the number, and I can prove it, because if you add the number to the set of transactions, you get this very difficult to guess hash function with X amounts of leading zeros. I have found the number, and he communicates that number to the rest of the community. However, often the reason why they will do that, what would be the reason that you put all these efforts, all this electricity, all this computing power, all these efforts to find out this imaginary number, is that in many of those blockchain systems, when you are the first one to get the nonce correct, you will get a reward. In a blockchain net, in a Bitcoin network, for instance, you will get a little piece of blockchain of a Bitcoin to reward you. That's the reason why so many people are competing in that network, because they want to be the first one who finds out the nonce. Yeah? No, go. Yeah. The function of the difficulty requirement is to make sure that finding that is a very difficult exercise, because what you want to achieve is that guessing this nonce is, on the one hand, it may not be too easy, because if it's super easy, again, you can easily trick the system. You can make longer and longer and longer chains, and you claim to be having the truth. So it cannot be too easy, because then it's very easy to tamper the system. However, it can also not be too difficult, because if it takes you 10 years to calculate, to find out a code that is compliant with your difficulty requirement, what's the purpose of a system that needs to have you 10 years before you can add a little bit of information? That also doesn't work. So it's kind of a balance between not be too easy, not be too difficult, still allowing you to add chains after a few minutes, for instance, which is doable, which is not too easy, but also not too difficult. Of course, it also then depends on what is the current state of calculating capacity. We have seen that hardware systems, chips, they become ever more performant. They ever become quicker and quicker and quicker to do calculation, Moore's law, as we saw in the first session. So it also depends there, how quick are your systems in making those calculations, in coming up with a new number, calculating the hash function, checking, verifying whether the difficulty requirement is met, yes or no. If not, we start again. So how that is determined, that's a very technical discussion, which I will not open here, but the general idea is it needs to be something that is not too easy, not too difficult, and it requires people who want to add information to the blockchain to do some work. And the work is guessing a number, calculating the hash function, see whether it meets the difficulty requirement, yes or no. All right? Yes. Hash functions are often used to encrypt data because that's where it comes from. You had an original document. For instance, you have you buy a house, you have the certificate, and you want to have it to be stored, or you even want to have you have a secret document and you want it to be encrypted. Hash functions can be used for that purpose, because you take the input, the ones and the zeros, you have a very complex mathematical function, and based on those ones and zeros, they come up with that string. How that is calculated? Well, of course, that's an algorithm, that's a mathematical function. It takes all those ones and zeros and it does a lot of calculations with it, and in the end, it comes up with this string. Yeah. So hash functions, they do come from encryption, but here actually we use them for something else. A typical example, suppose that you make an account on a certain website and you need to have a password for that website. You only want that people who know your password, that they can enter the website. What is a very bad practice is that if I would be the platform and you register with me and you give me a username and you give me your password, that I store that password like that. If your password is I like dogs and cats, I should not store I like dogs and cats. Because if someone hacks my system, they read, okay, that person has this password, and maybe you have used the password on other systems as well. And so they have your password and they can go and do whatever they want. A smarter solution is that I do not store your password. I do not store I like dogs and cats, but I apply a hash function to it. I take your small piece of information, I apply the hash function to it, and I store only this code. This is much better because the next time that you log in, you go to my website, you put in your password, I like dogs and cats, I apply the hash function and I see, okay, I get this hash output. It's the same as the one I calculated earlier when you registered. So I'm sure that you provided the same input to me. You gave me your password. I can verify it because I stored the hash output at that point, and now I calculate it again. I see it's the same. So it's you. You can enter. But it also has the benefit when I'm hacked and that person gets access to the output of the hash function, okay, he or she has the output of the hash function, but as I said, it's a one-directional mathematical function. So based on the output of the hash function, I can never find out which was your password. I can never find out, or at least I should do a lot of attempts, a lot of brute force attempts. I should guess a lot and a lot and a lot before I would be able to find out that your password is I like dogs and cats. And by doing that, by not storing your password, but by storing the hash output of your password, I can remember your password, so to speak. I can verify it, while at the same time, I never store the password itself. So that's where hash functions come from in security. But here we use them a little bit different, but with the main reasoning. We have an input, we apply a very complicated mathematical function to it, and we get an output. And okay, if we apply different input data, we will get different output data. And the nice thing is, based on the output data, we will never be able to find out the input data. Yeah. No, no. So it's one directional, meaning that if you give the same input, it will always give the same output. That's needed because otherwise I would not be able to figure out that you have entered the same password. So what I want to do is to make sure that only you can log in, only you know the password. And so it needs to be the same information and it gives the same output. So it's one directional, but it's deterministic in the sense that if you provide the same data, the same output will be there. If you provide other data, another output will be there. But regardless of when or where you execute the hash function, the same input will result in the same output. I come in a minute with you, but this gentleman was a little bit earlier. It's something that you need to add to the block. Yeah. It will be there. It will be stored on database systems. And there's no, I mean, the only reason to change that would be that something in your block changes, because then you know the output of the hash function will be different. And then to have a hash function which is compatible with the security requirement, you will need to find out another nonce. So normally it will not change unless you're trying to tamper with the system, unless you're trying to mess up the system. It's not a property of the node. The node are the computers or the people participating into the, sorry? Yeah, then yes, but we don't do that here because in blockchain terminology, a node is a computer or a participant in the network, not a document. You could say indeed a blockchain is a chain of blocks and we say that a block is a node, but we don't do that here because that's confusing. The nodes here are computers in the network, not documents. But indeed, it's true that nonce is related to that element, so to speak, in the blockchain. It's related to a block. You also had a question. Yes? Yes. Mm-hmm. No, indeed. Yeah, well, if you apply, you can use it every time for the same block. So once you have found a nonce, you will use it at the same block, but each block will have a different nonce. So, okay, I could have changed the colors here. This one red, this one green, for instance, because the nonce itself will for every block be different, but for the same block, once you solve the puzzle, theoretically speaking, I think that in some algorithms you might have multiple nonces, but in most cases it will already be difficult enough to find one. So the first person or the first node who finds it will announce it, will claim the reward. It will be stored in the package of the block, and people progress. Because, as I said before, the only way to have another one here is because you want to mess up, you want to change this information. And as soon as you mess up here, you need again to start to find a nonce that has these compatible 11 leading zeros. Yes. Yeah. Yes. Mm-hmm. Yeah. Every time that the new nonce is or that the new block is added to the system, the game starts all over again. So if you used here a certain number and it didn't work, you can again use it there because you never know what it will be. All right. It's absolutely random. Yes. That's also the reason why it makes it so, well, on the one hand, honest, in the sense that if you have all the same computing capacity, then it's a very fair game because everyone tries at random and one will be the lucky winner. In reality, it's not so honest because some people will have more processing power than others, so they will be able to do more attempts quicker than others, and so they win, statistically speaking, more games or more rounds or more rounds because they are quicker because they have more capacity. But if everyone would have the same capacity, then it's a fair game, an honest game. And here was also yeah, well, you have the development of hash functions themselves is a very advanced field of mathematics, which is way too complicated for for my understanding. But you have these days the IS-256 algorithm is what is typically concerned as a hash algorithm that is almost not hackable, or that you cannot figure it out analytically. You need to add this brute force attack. But of course, as computing power increases, as Moore's law remains applicable, machines become more powerful and it might be easier to guess and hit the right answer. So the only way to keep up with that is to have more advanced hashing algorithms, or to make your to make, for instance, your output to require that it's longer and so on. But yeah, mathematicians and engineers are busy with creating new hash functions. To be honest, I don't know to which extent AI can actually help you with solving hash functions. It's an interesting question. I've never thought about it before. I don't think, with the knowledge that I currently have, that AI really helps in that. What can be very very helpful there is that like this field of quantum computing, that is kind of seen as a threat to these kind of hashing systems, because they are able to do a lot of a lot of a lot of parallel computations, and so I think these are a more near threat than AI algorithms. Yes. Sorry, they're becoming. In the end, you want to make them quantum proof, yes. But also there, to be honest, my knowledge of real quantum, I mean, I know the basics, but I'm not an expert in quantum computing. There might be a stage where the algorithms that we use now can be reconstructed in a few seconds by new algorithms. We cannot prove that it will never be possible, But then, of course, new algorithms will need to come up to make sure that, again, it becomes difficult to mess up with the system. All right. Thanks for being so patient in this not so easy explanation, but I think it's good, like to experience a little bit how it works, because if people now will start throwing stories or kind of applications to you, then at least you know a little bit what this is about and how it works. Of course, there's a disclaimer. This is a generally applicable model. There are many variants. There are many ways of working with blockchains. So don't take this as like this is always and everywhere the same. No, there are different versions, but this is a good start to understand the mechanism and the basic principles. Yeah. So where can it be applied? Let's make it a little bit less technical. We know, or you know probably, that blockchains are typically used to store currency transactions, Bitcoin, A to B, a certain amount. But you can actually store anything. So you can have value transactions, cryptocurrencies, and you have many cryptocurrencies, as you know. The idea is that you can have currency transactions without a central authority. Normally, if you have euros or dollars or whatever currency, and you want to exchange that value, either you need to have like touchable giraal, they say in Dutch, like you really need to have the paper in your hands, and that comes from a central bank who has printed it, and you can hand it out to each other. Or you need to go to your bank app and you can transfer money from one to the other, but then you use these central authorities. And the idea of a blockchain is that you don't need such central authorities. You do it on your own. But you can also do it to store documents. If you want to prove that a certain date you did this transaction, you made a certain contract with another party, you could store it on the blockchain and say, well, just as we prove that a certain value transaction has taken place, we can use a document, put it on the blockchain, make it verified, and then you can prove, well, on this date we have done another transaction. You can even go one step further and you can have smart contracts where you do not only store a document, you actually store some kind of an algorithm on the blockchain that's automatically executed if a certain condition occurs. Really, if this happens, then we will execute that, and you post it on the blockchain so that it's written there, it's fixed, nobody can tamper with it, and it will also be executed no matter what else happens. If the starting conditions are fulfilled, then the code will run and execute. But the general philosophy is always the same. We try not to have a central authority. We try to eliminate what's called the middleman. Does this ring a bell to something that we saw a few days ago? Sorry? SCM, yes. And what within SCM? What did we see there? Critical duration? Not really. Yeah, eliminating disintermediation. This is basically disintermediation on a technological scale, not in a supply chain management chain. Where does this come from? Well, as you might know, actually it's not that old. In 2008, during the financial crisis, there was this guy, Satoshi Nakamoto, who said, well, after this financial crisis, maybe we cannot just trust central banks anymore. We need our own system. We need an electronic payment system based on cryptographic proof, so these hash codes, instead of trusts, allowing any two willing parties to transact directly with each other without the need for a trusted third party. This has resulted in for instance, the Bitcoin is a cryptocurrency. A few days ago, I again looked at what the current value of it is. It's again covered in the news in the last few weeks and months. You see, it's highly volatile, but okay, if you would have invested in 2018, you might have made a very good investment, to speak the least. But it's highly volatile. It went up and then down and up and down, and so it's a tricky investment. You need a good stomach for it. And Bitcoin is the most well-known one, and there are many other currencies. There's a lot of dodgy and not so correct behavior there. A lot of new currencies are brought out every now and then. A lot of them, they appear to be a scam. So I love reading about technologies. I'm a technologist, but you really need to be careful with these cryptocurrencies. A lot of people with not so good intentions are there in the market, and they might try to be there not for the greater good, but mostly for their own good. Yeah. So there are some. I mean, it's a nice technology, but I have the impression that often people are overhyping it, because in essence, as I said before, it's nothing more than a database, and we already have many databases. The only difference is that now we don't store it in a central way, we store it in a decentralized way. And so the value needs to be in having it decentralized. Up to now, many organizations have been trying to figure out what possible applications could be, but yeah, we have not seen yet the killer application except for cryptocurrencies. And those have very frequent and important drawbacks, controversial points. The main benefit, not having a central authority, not having a central bank, is also a main weakness. Because what happens if your whole economic system would work on cryptocurrencies like Bitcoin? Well, there's no way that you can manage inflation, because Bitcoins are added based on the rewards that people get for adding additional blocks to the chain. But there is no way that a central bank can intervene and increase the amount of money, decrease the amount of money, manage inflation. Your benefit, the fact that there's no central authority that you can trust, also becomes your drawback, because there's nobody who can help you out if things go wrong. It's the algorithm who decides when additional currency is added. So this quantitative easing that central banks apply, no way possible with Bitcoin. There will be, I guess, 21 million Bitcoins at some point. That will be the maximum, and there's no way that you can increase the amount. Also, high volatility, what I said before, it sometimes really has the characteristic of a bubble. We also discussed this .com bubble last time. Well, the graph that you've seen, it really has a lot of similarities with that. In a lot of regions, in a lot of countries, there's still challenges with having legal recognition. You cannot use Bitcoin everywhere to pay, for instance. And now, a few months ago, there have been trackers launched on the financial markets where you can actually buy trackers following the value of the Bitcoin. But not everywhere in Europe or in the United States, you are just able to use actual Bitcoins, or as a business owner to use them for people to pay. There have been a lot of examples where Bitcoin cryptocurrencies were used for illegal purposes. Silk Road was one of those dark forums on the dark web where you could get all kinds of illegal stuff. It was driven by Bitcoin, and there were some currency exchanges like Mt. Gox and FTX, which were scams, were fraudulent. The processing capability. Although currently cryptocurrency is considered as the killer application for blockchain, but it more or less has 7 transactions per second, which is ridiculous if you compare it to the Visa network, which can have 25 or 30,000 times as many transactions. It has many forks. So today Bitcoin is used, but okay, it's still the predominant one. But every now and then you have forks, Bitcoin Cash, other Ethereum, and whatever who become more popular. There's a lot of environmental concerns about this technology, because trying to guess those nonces, it requires a lot of processing. A lot of numbers are tried, and then the hashes are calculated, and so on. So it uses a lot of energy, and depending on the reports that you read, maintaining the blockchain network requires more energy than certain countries as a whole. So there are some ethical and environmental considerations there as well. And you might even ask yourself, is it really more democratic? Because people say it's democratic, everyone can participate, everything is open and transparent. Well, this Satoshi Nakamoto, basically it's not a real name. It's the guy's name. We don't know who this Satoshi Nakamoto is or was, or maybe it was not one person, maybe it were multiple persons. We don't know who it was. What we do know is that apparently this person or this company or this group of people, they created in the beginning like roughly 1 million Bitcoins for themselves. So you have 1 million out of the 21 million that might ever exist that is in ownership, or at least was in the beginning of ownership of the guys who created this currency. So there are a lot of ethical reflections that need to happen in this context. Before we go to a break, I just want to briefly also zoom in a little bit on these smart contracts. Smart contracts are the same as other things that you can store on the blockchain. So instead of a document or instead of a transaction, you actually store a contract, which might say, well, in a certain condition, I will pay money or I will withdraw money and so on. So it's stored that if certain conditions are there, I will pay this amount of money, this amount of Bitcoin to that party. The benefits are obvious. Again, you don't need a middleman. There's no lawyer or judge who can say, well, now you actually need to pay. No, it's the network, it's the software who will execute it. It's transparent. Everyone can see the executable code on the blockchain, so everyone can see what's happening. It's deterministic. The code will be executed as it is programmed, but it also has some drawbacks. Yeah? If you have programmed the code wrongly, well, it will also execute wrongly. So if you have bugs, well, they are there and they can be exploited. It also means that lawyers who are typically not computer science graduates, well, those lawyers, they need to have also to gain that technical expertise. And at this point, it's very much experimental still. Nevertheless, there are some applications out there which you might know. The recent elections in the United States, I mean, you can gamble on everything these days. But for instance, one of the things you could gamble on was on who was going to win the US presidential elections. And one of the platforms that often used for that in the United States is Polymarket. Well, they use cryptocurrencies to do that, and they also use smart contracts. So they define a certain set of conditions, and based on that condition, well, if one of the parties wins, then if you have put your money there, then the smart contract says if this person wins, you will get the money. Mind you, this is not legal everywhere. For instance, as far as I'm concerned, or as far as I know, in Belgium or in Europe, it's not legal to gamble or to bet on outcome of elections. But the technical possibilities are there. Before we really go to the break, I want to show you one more example of a smart contract, and that's one of the experimentations that one insurance company tried. And it explains a little bit what these futures, or what the future of a smart contract. And this is also not a commercial break or whatever. VUB doesn't exist anymore. But I think it was a nice thought experiment, and they really tried it out and really saw, okay, what's the possibility here? And the nice thing is that you actually see a smart contract here at work. So you see some kind of a contract. The contract is stored on a blockchain. It's deterministic. So they have public databases where they say, if your flight is delayed, based on the information in that database, we will pay you an amount, and that amount is also agreed upon upfront. And so regardless what happens, there's a strike, weather conditions, whatever, it's the smart contract that says, if this plane is too late, this person gets at this moment in time this amount of money, period. Yeah? So again, it's experimental, and some companies use it. But yeah, this is how it might look at. Same is used for NFTs, non-fungible tokens. For instance, the property rights are exchanged or transferred on a blockchain. Yeah.